Okay, lovely people. We'll get started in half a minute. Okay, let's get started. Okay, today I want to go through the first principles of calculus. Okay, and this is how we get from an average rate of change, limits, and instantaneous rate of change. Okay, so it's a journey from the problems with average rate of change, using limits to get to a proper instantaneous rate of change. Okay, so let's get started. I think we might be able to use a bit of whiteboard marker than that. Okay, so if you have the function y equals x squared, okay, and I'm starting off with this function because this is probably the first function that you've seen and you'd be most familiar with as like an introduction to the curvy functions, okay? And if you have y equals x squared, okay, it looks like this, okay? And say you want to find out how fast it's going up at there, okay? You can use an average rate of change between, say, the point 1, 1 and 0, 0, okay? But you're going to get that gap. You're going to get the gap of being wrong, okay? And what the gap is the error in the thing, because the average is made up of the start, where you're going at a rate less than 1, and the end, where you're going at a rate more than 1, okay? And it averages to a rate of 1, okay? So it can create a little bit of a problem, okay? So we're trying to get around that point, okay? And what we're trying to do is find that one. A curve that just touches once and is parallel to that point. Okay? Now on a circle, that tangent is solved for us because the tangent is at right angles to the radius of the circle. But here, we've got a problem that the line is not part of the circle. It's a tangent to another function. So we're trying to find a tangent when there's no geometric rule that we can sort of base it on. So we're going to have to rest back on algebra. Okay? So we're trying to find a rate of change, and that rate of change is going to be m, which is made up of our rise over our run. Okay? And what we can do is start substituting stuff into this formula. Okay? So we're looking for the difference in y, for the difference in x. At that point, we're looking for how far do we go up for every unit we go across. Okay? So what some super smart people did is they started thinking, well, let's just have a look at what's happening around that point. If I take 2 points, and I'll start to do it on a different one, just because I think I'm cluttering that one up. If I take 2 points, say there and there, and I draw a line between them, I'm still going to have a gap. But let's just call this point 1. The gap, or the x value, h, and then this point 1 plus h. Okay? So what we've got is the point 1. We've got the point 1 plus h, and we've got the difference between them, which is h. Okay? And just by working out this point at 1, we can start to use it to give us clues on what to do everywhere else. And I'll just see if there's any questions. If there's any questions, just put them in. Oh, cool. If there's any questions at all, just put them into the thing, yeah? Okay, and so we've got 1 and our little gap of h and our 1 plus h. And we're trying to find m, the rise over the run. Yeah? Okay, so we know that this is still the function x squared. So we know that we can take away the y from this point and this point, and take away the x from this point and this point, and we'll get the rise over the run. So let's just have a look at what happens around there. Okay, you have your top bit, your m, which equals, now just for the top bit, this is x squared, or 1 squared. Okay, because you go across 1, you're on the function y equals x squared. So you've got your 1 point, which is x squared, or 1 squared. Okay, I'm going to move that to the other side, because you want to take that away from x plus h squared minus x squared, or 1 plus h squared minus 1 squared. And so I didn't write that really well at first, so I'll just go back and summarize. You've got your x plus h, which you're squaring. This point that's a little bit further along and a little bit higher is x plus h. This point that's back from it is your x. So if you take away x plus h squared minus x squared, you get that change in y. Okay, now this is really important to understand. The y is determined by squaring the x bits. So when your x bit is 1, it's 1 squared, or 1. When your x is 1 plus h, it's 1 plus h squared. And what we're looking at is the difference between these 2 points to find how much it goes across for every h unit we go up. Okay? So, that is all over x plus h minus x, or 1 plus h minus 1, which just the 1's cancel and we're left with h on the bottom. Okay, so this is our function. We've got 1 plus h squared minus 1 squared on h. And for every unit of h we go across, we're going to go up 1 plus h squared minus 1. Okay, so let's just expand this top bit out. And we're left with 1 squared plus 2h minus h squared plus 1, minus 1 squared. Okay? Now, these two cancel, and we're left with 2h squared over h. Okay? Now, on the top bit, we can factor out a h. Okay? So we're left with h outside of 2, because we've divided him by h, minus h, because h squared divided by h equals h, over h. Okay? And we can cancel these out. Yeah? So we're left with 2 minus h. Okay? For every unit you go across of h, you're going to go up 2 and across the extra h, or 2 minus that h. Okay? Now that may look weird, but it is very, very useful to us because of this fact, that if we take the limit as h approaches 0, we can make h as small as we can make it without being 0 in a mathematically rigorous and important way. And if we do that, we can say that as 2 minus h approaches 0, h approaches 0, and we're left with just 2. Okay? So on this function, x squared, I can say that the instantaneous rate of change of that is 2. Okay? This is like mathematically really important. Okay? I haven't done a great job of building your intuition before that, or maybe I have, and you will understand it. I don't know, because YouTube and no comments. But hopefully this is helping, yeah? Okay, you've got the point 1 plus h, and as 1 plus h goes to 0, there's almost no gap between them. But for every tiny unit of infinitesimal thing you go across, you go up 2. Okay, that's really important. Okay, I'll do another example with this x squared plus h, and hopefully it'll make a little bit more sense. But again, if you've got any questions, please put them in the comments, because I'm looking over at them to see if something pops up. Okay, and if there's a comment, if there's a question, I'm more than happy to answer it. Because again, like, I don't know how much we're getting or we're not getting. Okay, so just to recap, this is part of that x squared curve. Y equals x squared. And you've got the point 0, 0, and you've got the point 1, 1. Now, if we try and find the instantaneous rate of change at a point, and we don't have any cross bit to go up for, it could be anything. Because all lines go through that point and intersect with it. We're trying to find the gradient at this point. So this is what we can do. Okay? We can call this point x. Okay, we can do that. And this is solving the gradient from first principles. So we're calling this point x. We're calling a next point that's really, 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 really close to it, but not touching it, x plus h. Okay? Now, if this point is x, and the point that's really, really close to it is x plus h, we can chuck in x and y values for it. we can say that here's x squared, because x squared gives us our y value, and x gives us our x value. And we can say that this point is x plus h, and x plus h squared. Okay, so your x value is x, your y value is x squared. Your x value of the second point is x plus h. Your y value is x plus h squared. Okay? Hopefully that makes sense. Okay? Now, we're going to do the gradient between these 2 points as a limit as h gets closer and closer to 0. It's not touching 0, but it's a limit as it approaches 0. Yeah? And this is the definition, the background work for the derivative. So the derivative goes, or the derivative formula is the limit as x approaches, sorry, not as x approaches 0, as h approaches 0 of f of x plus h minus f of x over x plus h minus x. Okay, so the bottom is just going to give you h. H is going to be on the bottom. And the top is going to be your function that's giving you the derivative. Okay, and this is just like the y equals mx plus b. This is point x y2 minus y1, or y2 minus y1 over x2 minus x1, or x2 minus x1. And we're doing it as a limit as h approaches 0, as this difference between the x values of the points gets close to nothing, what's happening in the y. Okay, hopefully this is making sense to people. And I'd rather be telling you too much and over-explaining it than not explaining enough. Okay, so to do this particular one, you've got x plus h squared. So it's the limit as h approaches 0 of x plus h squared minus x squared, our function plus h minus our function, over h. X plus h minus x gives us h always. So you always end up with your h on your bottom. Okay, I expand this one, and I get x squared doing my FOIL plus 2x h plus h squared minus x squared. I've got him. Yeah? And all of that is over h. Okay? Now I can cancel some stuff. The first thing I can cancel is my original function, which is important. Okay, I can cancel out the x squared, so I'm taking away the x squared. And now I'm just focused on that difference, that growth between here and here, and gotten rid of the y value that was already there. Then I want to factor out my h. H, because h is in both of these, outside of 2x plus the h left over. all over h. Now, this is the most important step. As these two cancel, as it's a limit, this is something ridiculously tiny. This is something ridiculously tiny. But they both cancel out to 1. Happy with that? Okay? Even as they get ridiculously small and tiny to 0, they're both getting ridiculously small and tiny to 0. So they both cancel out to 1, and I can do that. Okay? This 2x plus h is what I'm left with. Now, as h approaches 0, the answer of this becomes 2x. Okay? So this is my derivative. And this is the first derivative I've worked out in front of you guys. This is our first derivative together. Happy days. Okay? And that derivative goes... the derivative of x squared equals 2x. Okay? And I've worked that out using first principles. This says find the derivative or find the rate of change for points along the graph. Okay? This says of x squared. And I'm saying that's 2x. Okay? Now, because I've worked this out with x and not numbers, it's a little bit harder, but it also means it'll work with any value you choose to chuck in for x. Okay? So you can see as this function hits the line and is 0, he's flat. Then, as it moves up to 1, it's at a gradient of 1. As it moves up to 2, it's at a gradient of 4. As it moves up to 3, it's at a gradient of 6. And it gets infinitely sharper gradient as it gets infinitely bigger and bigger and bigger and bigger and bigger. Because the gradient of the tangent to the curve is always 2 lots of your x value. And as your x value is infinite, so is your gradient. Whatever your x value is, your gradient at that point is double it. Okay? So you get an endlessly sharper and sharper curve. Hopefully that makes sense to people. Okay? So that's our first derivative from first principles. I'll recap that question and then I'll do the same thing with x cubed and we'll start to look at a bit of the pattern of it. Okay, so just to recap before I roll off the board, we're looking at x squared, but you can do this with any function. Your gradient for all places is made up of your rise over run. And that's how we find the average rate of change between 2 points. But what if we want to find out what 1 point is? Well, what we do is we pick the point we want to find, x, and we look at something that's infinitely close to it, x plus h. And we look at the limit as h tends to 0. Okay? So we can do that with the point 1. Okay, you have 1 plus h, you squaring, minus 1 squared. Okay, and that's all over 1 plus h minus 1, which just leaves you with h. Okay? Then you can square it. Oh, that should be plus. Okay? And you're left with 1 squared plus 2h plus h squared minus 1 squared. The 1 squareds cancel. You factor out the h and you're left with 2 plus h. The h from him goes and you're left with just the h there. And as it's h over h, that factors out to 1. And you're left with a gradient of 2. Okay? So we did that for values that are numbers, and we picked an easy number 1. Then we did it with x, because x represents all points. It looks very much the same, except instead of a 1, there's an x, but it works exactly the same. Okay? Any questions? Somebody want to put something in the chat? Nope. Cool. Okay. Just to point out, this is a derivative 2x. So if you're asked for what's the derivative, you do first principles and find the 2x. Say you're asked for the derivative when x equals 5. You chuck in the number because here's 2 lots of dx. Okay? Cool. Now instead of drawing the pictures, I'll move to a little bit of algebra. Okay? Just to sort of set you up for the thing. And drawing the picture with cubes is a bit hard, but hopefully the algebra will make sense. Okay? So, this is where we go with expanding stuff. If you have x cubed plus 3. So f of x equals x cubed plus 3. Okay? We put in the same formula, we expand the same way, and we should get the same result. Okay? Except this one will be 3x squared, because the derivative of x cubed is going to be 3x squared, and the 3 is going to cancel out. Sorry, I should have put a spoiler alert on that one. Okay? So, you have to use our formula, limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. Okay, that's our formula. We then go to substitute in our x cubed, and we're left with the limit. Sorry, I'll just move over here so I make sure I've got the space. The limit as h approaches 0 of x cubed plus h plus 3. Now notice I added h to the x. Ooh. And notice too that I should have the cubed on my brackets, because for all of these, h is added, then it's cubed. Notice too that I didn't add h to the 3, because that's not a function of x. If there was an x there, I'd go, like say it was plus 3x, I'd go plus h here. Yeah? But there's no x there, so there's no x or h there. You only add h's when you're adding. You just change the x's to x plus h. You don't actually do anything to numbers. Okay, and remember it's x plus h cubed, because x is now x plus h, and then all of him is cubed. Okay, and all of that is over h. Okay, now I need to expand him. Okay, I'm going to use the Pascal's triangle one, because it makes it a little bit quicker. Okay, so just remember Pascal's triangle goes 1, 1, 2, 1, 1, 3, 3, 1. 1, 4, 6, 4, 1. Okay. This is why we do the effort on Pascal's triangle. Okay, and I'm going to leave that up there because it is going to become important later on. Okay, but this expansion of x plus h is going to go x cubed because we've got our first coefficient of 1 plus 3x squared h. Remember, take 1 from his index, add 1 to go from 0 to h to the 1 for his index. Then plus 3x h squared plus h cubed. Okay? Then we're taking away, so that's that bit done. That bit is expanded to that bit plus the 3. Oh, I don't want to lose him. Minus x cubed plus 3. Okay, I know I'm a bit squashed, I'm sorry about that. And then all of that is over h, and it's the limit as h approaches 0. Okay? So that's all of this expanded. Now I can do the doffing. He doffs with him. Plus x cubed minus x cubed. The 3 doffers with that 3. So minus 3 plus 3, they cancel. Okay? And I'm left with this. Now because there's a h in 1, 2, 3, I can factor out my h, which is the important step. Okay? Three x squared, and the h goes outside, then plus 3xh plus h squared all over h, and that's the limit as h approaches 0. Now notice he cancels, and as h gets closer to 0, no matter how big this term is, there's going to be a value for 0 that's so small it makes that nothing. And there's going to be a value for h that's so small it makes that nothing. Okay, so they get cancelled as we approach 0. Yeah? They go away as h gets closer and closer to 0. So we're just left with him. Okay? The derivative, dy dx, this symbol here, or set of symbols, means find the first derivative of. And at the moment we're using the first principles to do that job of x cubed plus 3, and that equals 3x squared. Okay, are we happy with that? Any questions, or just check the string? Cool, nothing so far, which is good. Okay. I'm hoping this is making sense, because we're in lockdown, but no idea if I'm right or not. But I'm hoping that this is sort of clear and giving you the sort of the tools you need to understand what's going on. Okay. When you're doing first principles, the biggest one you'll probably get is cubed. Okay, I can ask you 4, 5, and 10, but that's just going to get really big on Pascal's triangle. Okay, like you can see, this is 4, and with 5, you've got 1, 5, 10, 5, sorry, 1, 5, 10, 10, 10, 5, 1. So with 5, or to the power of 5, you've already got 1, 2, 3, 4, 5, 6 terms, and you can see that the paper and the calculation in that is a lot of writing for not much extra complexity. So with first principles and proving it this way, the biggest job you'll get is probably x to the 3. Like we do 1, 2, and 3 with that. And then no more. So I'm going to do some number. I'm going to do x to the 1 with a coefficient, just to show you that this is the simplest one. We started with squared, which is a little bit more complex. But while this is up, I do want to hint at what the shortcut is. Okay, so I'll tell you what the shortcut is, or hint at it, and then sort of probably do one more. Okay, so this is the shortcut. What you'd see with the first one, the squared, is that only the second term in the thing mattered. So in the squared one, this was 2xh. Yeah? Now it's the cubed one, and only the second term matters. Okay? Now the first term goes to journey. This x cubed goes to journey because he's part of the original question. And always part of the original question. You're getting rid of this first term, this first power in a power series. Okay? Everything else has got h to the 2 or to the 3 or to the 4. So they get doofed as h goes to 0. And you're just left with this second term. Okay? This second term in the sequence. He's going to be the derivative with like powers. Okay? So the key thing is to focus on that. Now notice too, the index is 1 less, and the coefficient is the same number as the power. So this was squared, and the new coefficient is 2. This is cubed, and the new coefficient is 3. Okay, so follow that pattern too. But I think I might leave that there. That was first principles. That's 2 questions worked out with first principles. I would remember, first of all, the formula here. Okay, understanding that this is a formula based around limits, and that you need to write the limit out and get that is really important, and doing the calculus and the algebra. But that's the main principles of first principles that we're looking at this week. Cool, I'll end it there if there's no questions, but bye guys.